Okay, welcome to the final lesson of Integrated Math 3. It's not really a lesson. So everything you have already learned except one more thing. There's one thing left in this lesson that you haven't learned yet. And it's pretty obvious. Everything is obvious when you're working with statistics. Because you've already done everything in your science class. But we're just going to analyze this for now. And the mean of the treatment group is denoted as the x line of treatment, and the x line, or the x with a line on top, of control is the mean of the control group. So the mean of the treatment group and the mean of the control group. Find the x with the line on top for the control and this treatment group. So it's obvious, right? Just 3 plus 7 plus 8 plus 2 plus 6 plus 5 plus 3 plus 12 divided by 8. Get you, that's 10, so 20, 33, no, 31, 34, and 46. So 46 over 8 is 5.75. That is the mean of this group. However, this treatment group, now we have 5, 1, 2, 3, 1, 6, 2, 5. 5, 1, 2, 3, 1, 6, 2, 5. Divide that by 8, that's 25 over 8. Which is then becomes my 3.125. I'm sorry about the noise. It's the last lesson. People are getting excited. Is it 3 point? Yeah, it is. It's 3.125. So the last thing ever that you have to remember in this whole entire course is the experimental difference. The experimental difference is what impact the treatment had to the control. So whenever you're doing an experiment in science, you want to know what happens. You want to know what's the different when you change a variable. How does the whole thing change? How does the control change? How does the thing that you measure change? Right. So in order to do that for these types of experiments, you would calculate the experimental difference, which is the mean of the treatment, subtract the mean of the control. So if you go back here, you will see 3.125 minus 5.75, 3.125 minus 5.75, 3.125 minus 5.75, 2.625, and this is your difference. So something got decreased. You could tell something got decreased in the data set. So we will go and work with these problems now in the book. So a randomized comparative experiment tests whether music therapy affects the depression of scores of some college students, and the depression scores range from 20 to 80, with scores greater than 50 being associated with depression. The control group has 8 students, and the treatment group also has 8 students. The tables show the results. Find the mean score of the control group. So the mean of the control group is you add all of them together. I'm just going to do it in my head. Mean of the control. The mean of this control group is 49, 45, 43, 47, 46, 45, 47. Okay, so the mean of this control group is 46 as a depression score. And then the mean of the treatment group is 39, 49, 41, 40, 39, 39, 1, 1. I'm just saying random numbers. So it's 39, I think. I think the mean is 39 or 40. It might be 40. Okay, I'm just gonna do this. 3, 1 minus 3 minus 1 minus 1 plus 1 plus 2 plus 3. I don't know what I'm doing, by the way. Okay, so I'm just gonna add all of them together. 39 plus 40, 79, 118, 155, 155, 196, 236, 278, and 321. So 321 over 8, which is roughly 40.1. 40.13. 40.1 is our treatment group, and control group's 46. So what's the experimental difference of the means? Well, you take your treatment group mean, 40.125 or 40.13, subtract 46, you will get minus 5.87, 5.9, and display the data. And nope, not doing that. Double dot plot. The dot plot is just like this, and you could basically just put 30. I really could do this, right? And then 46 or something, and then you would place all your data points. But I'm not going to do that because you should know how to do that from 6th grade. And what can you conclude? What I can conclude is, well, the data doesn't have that much variation in it, so our mean is a nice mean. And we can conclude that even if you calculate margin of errors, it would be pretty nice. Well, if you calculate margin of errors, there would only be 8 people, so the margin of error would be pretty large. Therefore, you can't really use the margin of error as something for everything. For this, you can't use the margin of error because it's a smaller population, right? It's a smaller population, so it's a little bit less, right? It's for students. It's for university students, I think. Well, it's for students, college students, not for the whole world. Therefore, or college students only at that particular school. So the margin of error is usually just the amount of students divided by the amount of or like the amount of students compared to the amount of students in the college. So I can conclude that it's pretty clear that the treatment group is lower than the control group because the means the standard deviation of both are pretty small. So it's pretty clear that treatment works. Okay, number 9. To analyze the hypothesis, use the histogram, which shows the result of from 200 resamplings. Right, music therapy has no effect on the depression score. And compare the experimental difference in exercise 3 with the resampling differences. Does music therapy have an effect on the depression score? So the mean difference is new treatment subtracting new control. Our minus 5.87 doesn't even show in this graph. As you can see in this graph right here, our minus 5.87 is right here. It doesn't even show in this graph. Most of the stuff, actually most of the data points are to the left of the mean, to the left of the mean of the mean, the mean of the mean difference, and some data points are to the right. Well, not the mean of the mean difference. I mean the zero, right? The zero score, right? The mean difference of 0. So there is there is slight, if not none of, if there's slight if not no effect on the depression score in this case. But if you compare it with the experimental difference in exercise 3, then it's a way off anomaly, basically is what I'm trying to say. So therefore, if this was the 200 real resamplings of the plot, if this was 200 real resamplings, maybe there's a difference. You have to take care of all the different variables. Maybe you're only sampling college students, so maybe they are somehow more associated with music. I don't know. But if you're just sampling 200 random resamplings in a program, obviously this is probably going to happen, and the treatment wouldn't work in this case, right? Same thing with this one. Compare the histogram in exercise 9 to the histogram below. Determine which one provides stronger evidence against the hypothesis, and explain. So the one that determines the stronger hypothesis is the one that does the hypothesis the most times, right? It's not either or. It's the one that does the hypothesis the most time. And in this case, well, compared to the rest of the population. This case, the zero line lies somewhere here, and there's 23 people right on the zero line. This is a zero line. Zero line. There's 23 people in the zero line compared to the rest of the thing. This thing, there's one person on the zero line, right? 1 plus 2 plus 3 plus 2 plus 3 plus 2 plus 2 plus 1 plus 1 is 1 over 20, which is 5% roughly, right? This is 1 over 20, which is 5% of the population that has this hypothesis, and this is 23. But this is 23, right? 23. If we give this a range, for example, one away, right? So let's say this is the one line right here, about halfway in, and about halfway in, and we'll count every single thing. This is 23 over 200, which is way higher than the 5%, right? Way higher than 5%. Here, we're going to include everything now within one unit. So this would be so this is the 1 unit up and the 1 unit down, right? In this range, it would be no effect. Let's say, right? So 2, 1, and 3. That's 6 over 20 or 30%. Now we'll count all of these. 25, 23, 14, 16, 17. That's 20. No. That's 40. And that's 30. Which is 40 plus 30 is 70. And then add that to the 26, I think. So 96 over 200, which is 48%, which is which is more, not necessarily way more, but more than the 6 over 20. So therefore, this music therapy has no effect on the depression score. The stronger evidence will fall to this graph rather than this one. And final question. Without calculating, determine if the experimental difference is positive, negative, or 0. So just like how I did it with this, kind of calculating where the 0 is probably, where the 0 probably is, we can also do it the same, but for the mean. So the mean is probably, I don't know, right, the mean is probably about right here, maybe a little bit closer. It's around in that range for here. But for the treatment group, the mean is probably around right here. So you could see that the mean of this and the mean of this is like just by measuring the center, you could see that the two means are different, and the treatment group's mean is smaller than the control group mean. Therefore, the experimental difference will be negative, and the effect of the treatment is it lowered something, right? It made something worse. It might have made something better. It might have made something better as a result of making something worse, but that's it, right? So that is it. That is it. That's the end of Integrated Math 3. And thank you for watching this whole series. I don't think you actually watched this whole series. But thank you for staying with me in this arduous journey. I started it on February. I started February of this year, making these videos for the Integrated Math 3, and it's been quite rocky at times because I took a few weeks hiatus at sometimes trying to make this series. The next series that I'm going to make will probably be calculus, and it'll probably be a lot less rocky than this series, but I'm not too sure about that yet. I'm not too sure if I'm even going to make the calculus series, but if I do make one, it'll probably be calculus. So that's going to be it for the whole of Integrated Math 3. I hope you do good on your final exams. Whatever video you watch, whether it's going to be statistics, I'm pretty sure statistics isn't going to appear nearly as much on your final exam, but in the SAT or the ACT, they really like to add the statistics in there because of the real life applications that it has to go with it. So that's that's basically what I'm going to that's basically what I'm going to leave it at. And the just finished. The next course that you take, you can maybe argue over in the comments. But in my opinion, if you have really understood the material really well, you can take calculus as your next course after integrated math 3. Depends on if you're in the honors or the advanced or the beginning, or the honor or the advanced, or maybe you're just in the regular class. If you pull out a really good grade in any of those classes, I would say you deserve to be able to be moved to calculus. However, I know that some of your schools do not allow you to move to calculus just like that too swiftly, so you have to stay in the pre-calculus, and that's completely fine as well. And if you are struggling in any of the content in the Integrated Math 3 series, please leave a comment in the appropriate video. I'll probably go and check to this ending's lasting too long. So I'll probably go and check the video for what to explain, right? Because I want you to pass your final and stuff. If you're struggling, please tell me the video. I originally made this for people who excel, and I originally made this for people who, if they would finish this course, they would be able to go to calculus. But I know that some people can't do that, and I know that some people, not everyone's good at math. In fact, a lot of people are average. So I want to cater to the average people as well. So um, I don't know when the next time I'm going to be uploading a math video is going to be, except for the pre-calculus review that's going to come up sometime later this week, or maybe it already came up. So that's really all I'm going to be. I can't say see you later because I'm not going to see you later. I'm going to see you in a long time.